A very good morning to all of you. So I cordially welcome you all for this engineering thermodynamics course. So today is the last classroom discussion topic, that is the CTT 40. So it is the last topic in your thermodynamics syllabus. So the topic is the representation of the Stirling cycle, Ericsson cycle and Atkinson cycle on PV and TS diagrams. So the motivation is it is important to analyze the Stirling cycle, Ericsson cycle and Atkinson cycle on PV and TS diagrams to assess their performance. And what is the outcome from this lecture? So you should be able to analyze Stirling cycle, Ericsson cycle and Atkinson cycle on PV diagram and TS diagrams. So here, first of all, let us deal with the Ericsson cycle. So Ericsson cycle is invented by Ericsson, that is a scientist. So it is very, very important to know what are the various processes which are involved in the Ericsson cycle. So from this PV diagram, you are able to see, so there are the two isothermal processes are there. The two reversible isothermal processes are there and two constant pressure processes are there. So two isothermal and two constant pressure processes are there in the Ericsson cycle. So it is a representation of the Ericsson cycle on TS diagram because it is a PV diagram and it is a TS diagram. So here you have to remember, so the Ericsson cycle will consist of two isothermal and two constant pressure process. So how can we find out the efficiency of the Ericsson cycle? So efficiency of the Ericsson cycle is also similar to the T1 minus T2 by T1, which is exactly equivalent to the Carnot cycle efficiency. Because the Ericsson cycle is also containing all four reversible processes. That is the reversible isothermal process 2 and two reversible constant pressure processes. So all four are basically the reversible processes. So that's why its efficiency is also equal to the Carnot cycle efficiency, that is T1 minus T2 by T1. Next one is the Atkinson cycle. So Atkinson is also a scientist who developed this Atkinson cycle. So what are the various processes are there on the Atkinson cycle? So here you are able to see there are two reversible adiabatic processes are there, and one is constant value and the next one is the constant pressure. So constant value, constant pressure and two reversible adiabatic process. These are the Atkinson cycle. That is, it is simply replacement of the Otto cycle. That is a constant volume heat rejection is replaced by constant pressure heat rejection in case of the Atkinson cycle. That is, the remaining one are exactly similar to the Otto cycle. That is, here it is a reversible adiabatic compression and it is the constant volume heat addition and the reversible adiabatic expansion. But in the Otto cycle, we are having the constant volume heat rejection. Now here it is replaced by the constant pressure heat rejection process. Like that, we can differentiate the Otto cycle and Atkinson cycle. So similarly, so this one also will give you the same efficiency. So that is, the efficiency value also will remain same. So the next one is the Stirling cycle. So Stirling is a scientist who invented this Stirling cycle in the 1827. So here also, how can we represent the Stirling cycle on the PV diagram and the TS diagram? So what is the difference between the Stirling cycle and the Ericsson cycle? So in the Stirling cycle and the Ericsson cycle, so the two isothermal processes are same, but in the Ericsson cycle, you are having two constant pressure. But in the Stirling cycle, the two constant pressure processes are replaced by two constant volume processes. So that is the difference between the Ericsson cycle and Stirling cycle. Because the air engines, because normally the air engines are very, very important one. So that is to predict the performance of the air engines, all these particular cycles performance is very, very important to know. That is, how can you calculate the air standard efficiencies of all these Stirling cycle, Ericsson cycle and Atkinson cycle. So the Stirling cycle is basically consisting of two reversible isothermal process and two reversible constant volume processes. And coming to the efficiency, so the efficiency is exactly similar to the Carnot cycle, that is a T1 minus T2 by T1. So here the regenerative Stirling cycle has the same efficiency of the Carnot cycle. That is important one. So even though it is having the same efficiency, but they are having much less back work. So the back work is very less compared to the Carnot cycle, even though the efficiency of Stirling cycle and regenerative, the Ericsson cycle, Stirling cycle, and Carnot cycle will have the same efficiencies, but the Stirling cycle, Ericsson cycle will have the less amount of the back work. What is the reason? What is the reason? So hot air engines working on these cycles like Stirling cycle, Ericsson cycle, and Atkinson cycles have been successfully operated, but it is difficult to transfer heat to a gas at high rates since the gas film has a very low thermal conductivity, because the gases are having lower thermal conductivity values. So that's why it is very difficult to transfer the heat. So there has not been much progress in the development of the hot air engines. However, since the cost of IC engine fuels is getting expensive, this may find a field of use in the near future. So because of we are day by day, so we are basically avoiding this particular the IC engines, because nowadays the petrol engines and diesel engines are now getting replaced by the electrical vehicles. And similarly, the air engines are also there in the past, but still, because of the depletion of the fossil fuels, now this particular the hot air engines once again they are coming into the picture. So then automatically we can find the usage of this particular the Stirling cycle, Ericsson cycle, and Atkinson cycle. So thank you very much for attending this particular class on the Stirling cycle and Ericsson cycle and Atkinson cycle. So with this, we are able to complete our syllabus on engineering thermodynamics. I hope you understood the concepts of the engineering thermodynamics. The only thing is that now you have to apply the concepts of the engineering thermodynamics in our day-to-day, the practical applications. So then only you will find the beauty of the engineering thermodynamics concepts and fundamentals. So I am wishing you all the best for your future. So thank you one and all for listening all the classroom discussion topics and all the self-learning topics which are related to the engineering thermodynamics. I wish you all the best. Thank you.